I think it is a very common topic for all of us, Newton's laws of motion. So Newton's laws of motion, I think you have already covered it. If it is fine, then otherwise we have to take up little that way. So in this context also, we would like to see one thing very closely related with this motion. Swamiji is mentioning that external motion we call action, internal motion is human thought. We are going to discuss the motion in the external world, and that is known as action. And we are having internal motion in our brain, in our mind, always something is going on. We are discussing with us, or sometimes we are analyzing something. So in our mind, we are having two persons talking each other at every time nearly to say. So that is human thought. It's also a motion. It is also required, but it should be directed to a positive thing in order to realize the goal of our life. Now, Newton's first law of motion, I would like to start with that. So Newton's first law of motion, first to know in which book he published his 3 laws of motion. In which book Newton published his 3 laws of motion, and also what was the language. Write it also in your copy. So Newton published his book. Initially it was 5 laws, then he summarized, or it is made compact and into 3 laws. So the laws are written in the book name. If you translate it into English, it will be known as Mathematical Principles of Natural Philosophy. The book was written in Latin. The book is commonly known as Principia, because Principia is one of the word here. So this is the book and the full name of the book and the language. Earlier days, generally the books were written, or scientific things are written in Latin or German, sometimes like this. Nowadays, many journals are coming up in English and also in some vernacular languages. So these are the way how we publish some research papers. The first page of the front page of this book. So front page of this book, where we can find Newton's 3 laws of motion. Now we would like to first start with the Newton's first law. I think you have studied, but I would like to start with one experiment. First, see the experiment to understand what we can get the idea from here. Check this one, the experimental procedure. So there is a one tablecloth upon which some utensils are kept. Then our teacher is going to drag the tablecloth towards him. The question is, what will happen if he drags the tablecloth towards him? So what will happen to the utensils when he drags the utensils towards him? First, Vijayawada. I would like to see the experiment. So first we go for that experiment. Yes, so that happened. So utensils remained in the same place. But why? Why? So we have to understand that thing. I would like to start with first the law, what Newton proposed. The law is this: an object at rest tends to stay at rest for eternity. An object in motion tends to stay in motion unless acted upon by an unbalanced force. So the last point is there. If we do not put any unbalanced force, there will be no change in the phase or in the state of the body of rest or motion. If it is a body in rest, it will remain a rest for infinite time. And the body is moving in motion, it will remain in motion in straight line with the same uniform motion or uniform speed. But if there is a force, it can change only. Otherwise, it will remain in the same state. So this is the very basic idea from the Newton's first law. Very carefully note the points, note the ideas, and then we will go for the discussion also. So this is Newton's law, and this is Newton's first law of motion. So Newton's first law is like this. Then we will come to this another experiment. Suppose the table is now long, and if we want to perform the same experiment, dragging the tablecloths towards the person, keeping several number of utensils one by one. So what should be the result at that time? What will happen with the utensils? So when we can perform the dragging of the tablecloth or the pulling of the tablecloth, at that time utensils will not fall because the friction will be very small enough and we can do it quickly. But if the tablecloth is long, then pulling up this or dragging the tablecloth towards the person will take time, and also the friction will be more. So at that time, there is every chance at least few utensils will fall down, if not all. So this is one type of force restricting us to do the same thing what we can do in small table. So there is a visibility, or there you can see one thing which is known as force. Now, if we go for balanced and unbalanced force, suppose a truck is trying to move. If there is a 100 Newton force in this motion, and another force is applying on it in the reverse direction, and 100 Newton, so for truck cannot go. It will remain in the same position. If the smaller force is acted upon that, then it can move, but slowly, but still it will move. So this is balanced and unbalanced force. This is the thing we have to understand. From the Newton's laws of motion, we can see many things. And then to understand, I would like to show one animation. Nowadays, we are very much familiar with one thing of the rocket launching. Chandrayaan-2 has already been launched with the help of our rocket. So in case of a rocket, when rocket is placed in the launching station, it is at rest. So if we ignite the fuel, so when we ignite the fuel, then it starts moving. So two types of things are there. One is at rest, one is at motion. I would like to suggest one of all of you to understand this thing. T, time taken 1 second, then S is the distance traversed. If it is 10 meter, in the second, if the distance traversed 30 meter, in the third second, if the distance traversed 50 meter, then what should be the acceleration? Is it uniform or it is something different? How to understand and how to calculate? You should go through that this way. So we are only concerned about now the motion. So motion can be changed. So one at the rest, and then at the time, one thing, and in another time motion is there, and motion can be also changed. It can be accelerated also. So these are the things here. Newton's first law, we can go for explanation of all these incidents. Newton's law is also known as law of inertia. I would like to come with the inertia, I think. So inertia, now from here, a body remains at rest or moves in a straight line at a constant speed unless acted upon by a force. So body remaining at rest, it is rest, inertia of rest. And when it is moving in a straight line with a constant speed, uniform speed, that is inertia of motion. So this is the very basic nature of the body to keep in its own inertial position, either in motion or in rest. So this is inertia. That's why the first law giving us an idea of the inertial nature of the body. whether it is at rest or at motion. So Newton's first law, from here we can get this idea. You take up some simple examples, and whatever we can find in our locality also we can, and also in our action also we can find all these things are here. So from this we can get the idea of Newton's first law. Now next, to go for that, now few questions, very common things. In a library rack or in our study room rack, if we keep books, sometimes it is sliding and falling down. But we do not find that it is going on for all the time. It will certainly stop at a time. So if Newton is saying that if the body is at motion, that it will remain for motion, and if body is at rest, then it will remain for rest for all the time. So if objects in motion tends to stay in motion, then we are not getting this type of things. In case of sliding of books, or ball is thrown upward and then falling back also. I think the idea is very simple. So these are not keeping in that same position or same state of motion, because there is something unbalanced force is there. So book is sliding across a table, slows down because there is a friction. So we do not find the books are falling forever. It will stop even for within few seconds also. Similarly, ball thrown upward also come down due to the gravitational pull, and ultimately it stops. So these are the things we find, this type of things. I think very simple idea. You can understand these things. It is in our, sometimes we can also find in our life also that books are falling or some things are falling. And we are also practicing when you catch a ball to throw up and to get it back. So all these things happen. Now inertia, once again, the resistance of an object to change its state of motion or rest can be termed as inertia. It is the basic property of the body. When you say object or body, you can take up into simultaneously some. And so inertia is the basic property of the object, trying to keep its state of rest or of motion. Then inertas, the word, Latin word from where it is coming, very funny thing that the meaning is lazy. And sometimes it is said for a lazy person that you are at the inertia of rest and need not to change. So inertia of rest is, Newton took up the idea of the inertia of rest first. And we are always inertia of rest. We try to tend it that. We do not like to move, work hard. So this is our also basic property, so to say. So we have to cross it. So inertia of rest and of motion. It is the basic properties of the object or body. Now, in case of changing this one, larger force may be required. Smaller force can also some way. So when to apply smaller force and when to apply larger force. And if we can change the state with a smaller force, at that time, if we apply larger force, then what will happen? Can we get something different? So these are the questions you have to answer. In this occasion, we have to, again, to look back. Friction in the first example, first experiment we have seen. A force that resists the motion. Air resistance and sliding on the rough surfaces. All are examples of frictions. So friction, in the longer table, we could not do the same type of experiment what we did in case of smaller table because of the friction, as you told. So friction is one of the resistance force here we can find. This is also a force. Now, I would like to pass one simple example, what we find day-to-day life. Then my question is already there on the top. I would like to get the answer from Vijayawada first. Why should we always wear seat belt while traveling on a car? Vijayawada, what is the reason behind it? Why should we do that?
To be in inertia.
So if we find that a moving car is stopped suddenly, then what will happen? Car will stop. But the passenger cannot stop immediately because they are on the same motion. And there is every chance of accident. How to avoid that? If they wear the seat belt, then they will be certainly stop at the same time and can avoid the accident. So this is the thing. Why should we always wear that seat belt? Now, next one. I would like to get the answer from the salt for that. So these are the things we have to. We can check this one when a hanging carpet is bitten by a stick or with a stick. So dust particles remains in the state of rest, and so it will fall down because the carpet is moving when you beat it. So why do we beat carpet to clean that instead of sweeping? These are the simple things to remember. We have to go for this. So you can take this type of action some other places also. I would also like to show you another example also. So beating of carpet to clean it instead of sweeping. Now another thing, why do we sometimes collect fruits by shaking a tree? Salt Lake 9A. Salt Lake. If we can generate a different type of inertia in one body, then other things remaining on it will fall down. So this is the thing here. On shaking or jerking, in every tree we cannot do it, whether in case of some soft trees and also having soft petioles of the fruits, only we can do that time, not in every occasion. So at that time, if we put jerk, then fruits will fall down because of the fruits want to keep in the state of rest while the plant is little moving. So that's why the fruits will fall down. These are the things we find it. So shaking of this tree, sometimes we can get fruits and collect it quickly instead of mechanical plucking. Now, these are the things. Now, what is mass? Mass is the quantity of matter present in an object. We would like to have a little simple ideas with that. And then, so measurement of inertia also. If the mass of the body is more, then inertia is more. You would like, then you should have more amount of force to change its state of rest or motion. So measurement of the inertia also depends on mass. It should be the measurement, mass is measured in the unit, in SI unit is in kg. I would like to ask you, kg, 2 letters are there, then all the letters in small letters. What is the reason behind it to make all the letters small? Can we not write any letter in capital? The rules behind writing the unit kg, the unit should be written in capital letter if it is given upon the name of a scientist, like Newton, like Watt, like Kelvin, all are. Then at that time it should be capital. If it is not, then it should be in small letter. Like gram is not based on scientist name, so it should be small letter. But not about the K. K is the prefix. Try to remember. K is the prefix, like millimeter, milli is the prefix, centimeter, centi is the prefix. So milli, centi, deci, deca, hecto, kilo, all are prefixes. So milli to kilo, all the prefixes should be in small letters. This is the rule. Beyond that, like mega, in case of megawatt, M should be capital and watt, as it based on scientist name, both are capital. So beyond the kilo, all prefixes should be capital, like megawatt, terawatt. All these things are in capital letter. This is the rule. You should follow it. So measured in kilograms kg. Now weight. Another idea we have to still remember: weight, the force upon an object due to gravity on Earth, and in other cases, the in gravity of that places. So weight is mass into acceleration of gravity. This is the relation between mass and weight, simply known as W into mg. I think you can still remember the equation: W equals to mg. So mass and weights are required. Measured in Newton, weight, the unit of weight, or actually unit of force, is Newton. As weight is also a type of force, so the unit is written as N, and N capital, as it is based on renowned scientist Newton. So Newton is this, Newton. Now I would like to pass to one test. I think we can now go for a test. So far we have discussed several things. I would like to put 4 locations: Earth, Moon, Space, and Earth Center. Suppose an astronaut has started his journey from Earth carrying a bag whose weight is 180 Newton. So an astronaut has started his journey with a bag of weight 180 Newton. Then what should be the weight in other 3 places? What should be the weight in other 3 places? APJ Salt Lake 9A first. 9A. This one, we are observing now that spaceship from the Earth is going towards the International Space Station. It is going to be attached with that. International Space Station is a satellite, artificial satellite like spaceship. It is moving around the Earth in every 90 minutes. So the astronauts from the Earth is going towards to join the International Space Station. Check this.
Is sent up from Earth.
Soyuz heading toward a link up with the International Space Station, now 20 meters from docking.
By the time the 2 craft dock, they are traveling at over 28,000 kilometers an hour.
Standing by for contact.
Okay. We have contact.
We have initial contact of the Soyuz capsule to the International Space Station.
So contact has been made, and from this space, we can see our beloved Mother Earth as a blue planet. So it is now in front of us, blue planet Earth.
Things have moved on since Phileas Fogg took 80 days to circumnavigate the globe.
So 2 hours back, these astronauts can move on their feet, but now they cannot move. They can float. They can keep themselves wherever they like. So this is the condition of weightlessness. I would also go for a little more. Check this one.
These days, the crew aboard the space station circle the planet once every hour and a half. Obviously, the first thing they'll have to get used to is weightlessness. As one aspect.
So on Earth, if we inadvertently, even if we cannot keep a glass, and if it falls down, there is every chance that we will be rebuked by our seniors. But in space, there is no chance of it. Even if it falls down, it will not going to break because it will float. So everything is floating wherever it is, wherever you keep it. So this is the thing what we find in case of space. Look at also.
This experience of weightlessness gives the astronauts real insight into how the world below got to be the way it is. Any liquid spilt on the space station starts off as a wobbly blob before magically drawing itself into.
So even the liquid droplets are in the state of float, in a state of floating nature. So it will also float. This is known as weightlessness condition. There is no unbalanced force to change the state. So here in every occasion, if we want to put our answer in the table, we are going back. In the moon, that will be 30 Newton, certainly. In space, it will be 0 Newton. In Earth center, it will be 0 Newton. Now, what should be the mass in every occasion? What should be the mass in every occasion? Vijay, I would like to get the answer from you. So 18 kg, now coming back to the 18 kg, so it is 18 kg everywhere. It will be 18 kg everywhere. Our calculation should be done on the basis of W equals to mg. So mass and weight, from here also we can identify or understand that mass remains constant all the time, while weight can be variable, even it can be 0 also, if there is no unbalanced force, like in space. If we go for the next one,